Nomenclature. So you know how to do this because you did it on your summer packet. We did it consistently throughout Honors Chem. All we're going to do today is just remember how to name ionic compounds, covalent, acids, and hydrates. Hydrates are maybe a little bit new, but there's nothing really difficult about this. So we'll blow through it, and then you'll just answer some questions. Naming binary ionic compounds. Binary means two. So it means that you're going to be naming a cation and an anion. Not necessarily a metal and a nonmetal, just a cation and an anion. The positive ion is always written first. It takes the same name as the element. So if we're talking about the potassium cation, that's how I name it. Potassium cation. Aluminum cation. The negative ion is written last. It takes the first part of its element's name and adds I. There is not a set procedure for where to put the I, like oxide, fluoride. There's no specific spot. Carbide, nitride, phosphide, sulfide, chloride, bromide, iodide, sort of selenide. You have to just kind of hear it and figure out where to put it. And so it gives you the example there. What do we use for the transition elements, or any element that we don't know the common charge for? What's that called? The stock system. The stock system is where you're going to use the Roman numeral to indicate the charge of the cation. We don't need to do the stock system for anions because we always know their charges. We know their charges based on the group number on the periodic table. So how many electrons does it need to gain in order to become a noble gas? That's how we'll figure out the charge of the anions. The cations, the same idea for the main body elements. Our representative elements, we could use the group number to figure out how many they lose. But the transition elements, or those other metals that are underneath the stepladder, they're going to get the stock system. So just remember that your Roman numerals are written in parentheses. They tell you the charge of that cation. We know the charge of sulfide is -2. This means copper must be a +2. Make sense? Okay. Naming binary for stock system again. We know bromide's a -1. You look at your periodic table. Copper must be a +1. Fe2O3 is written as iron 3 oxide. Iron is a +3 charge. Oxygen must be a -2 charge. The other thing that we always are going to check is that our ionic compounds are neutral. So when we create these charges, if I do Fe2O3, which is what? Rust. So I can check. If there's two irons and they're both a +3 charge, that gives me a total of a +6 charge. If I have oxygen, there's 3 of them, and it's a -2 charge, and that gives me a -6 charge. So overall net charge will always be 0 for any binary or any ionic compound at all. You'll always be able to get the charge to be equal to 0. All right, so naming binary. Go ahead and name this list. So first thing that you should always be looking at is your periodic table. That should be in your face right now. And you should always ask yourself, first question is the first element a metal? Because if it's not a metal, then you're not using ionic naming. Then your second question should be if it is a metal, is it a metal that I know the charge for? And if it's not, then you're going to need to use the stock system and use Roman numerals. So let's just take 2 minutes to get through this, and then we'll come back and check. All right, so the first one, lithium fluoride. It is a common charge, so we don't need to use the stock system. Number 2, Tasya. Yep. Number 3, Emily.
Potassium sulfide.
Yep. Number 4, Mike. Whichever. Yeah.
Iron 2 sulfide.
Iron 2 sulfide. Correct. So let me just quickly throw this one back up here so that you remember. If I have FeS, one of the easiest ways to do it is just recognize that the charge on sulfide is -2. Since this has to be always equal to 0, the net charge, it's -2. There's one of these, we don't write ones, and I'm trying to find the charge of this. So it's like saying 1x or just x, -2 equals 0. So x must be a +2 charge. This is simple for this example, but remember you're always looking at overall net charge being equal to 0. So iron 2 sulfide. Number 5, Allison.
Magnesium.
Yep. Number 6, Michaela.
Manganese 2 oxide.
Yep. And number 7, Olivia.
Copper 3 iodide.
CO.
Oh, gosh.
Cobalt. Cobalt 3 iodide. All All right, next. Naming with polyatomic ions. Always use the name assigned to it. Do not add additional suffixes such as "ide." So you just have to memorize your polyatomic, which you did already with me. You just have to kind of recall those. So carbonate, CO3 minus 2, is a carbonate ion. We'll go through a list of polyatomic ions today. There's a few additional ones that you're going to need to know. I honestly think it'll be easy for you because you're so used to doing it with me, but some of you had me a year ago. So if polyatomic ions are a little tricky for you to remember, you can take out that list that I gave you in honors and review them. And then you can always use Nick the Camel. Remember that? Nick the Camel ate a clam for supper in Phoenix. So you use all the main words to give you your subscripts and your charges. If you want me to show you that again, stay after school today, and I'll go through that with you again. Otherwise, just memorize them. So ammonium is the only polyatomic cation that you need to know. It's the only one with a positive charge. It's NH4+. As a side note here, because we will do this throughout the year, we use ammonia tremendously at the end of the year and occasionally in the middle. Ammonia is NH3. Ammonium is the cation NH4+. So this is ammonia, and this is ammonium. So how do I remember which one's which?
Ammonia is shorter, so there's like.
No, I think ammonium. You do whatever tricks you want in your head. Ammonium, I think yum, 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 yum. I'm eating more hydrogen. So ammonia is your NH3 version. Ammonium is your NH4+ version. I'm telling you that this is one of those things that ends up tripping students up later on in the year because you write the wrong thing down. So ammonia is NH3. So when we couple ammonium as a cation, we can still use the same rules for ionic naming. Then this time your anion is going to be, it could be just a monatomic anion, or it could be one of your polyatomic anions. So you could have two polyatomics together, like ammonium nitrate. All right, hints for learning the names of polyatomic ions. There's only 3 polyatomic ions that end in "ide." It's cyanide, hydroxide, and peroxide. So peroxide's a new one that you'll need to know. It is O2 minus 2, which is where we get hydrogen peroxide from, which is H2O2, hydrogen peroxide. So O2 minus 2. Everything else ending in "ide" is a monatomic anion. So if you hear something ending in "ide," you know that that means it's either nitrite, oxide, fluoride, all of your monatomics, except for hydroxide, cyanide, and peroxide. All right, hints for learning the names of polyatomic ions. So hypo plus ite means it has 2 less oxygens than 8. So let's go backwards for a second. There's the 8 and the ite version. Those are always for oxygen-containing compounds. So if it's ending in "ide," it's those 3 that you just saw in the last slide. Otherwise, you have 8 and ite. The 8 version always has how many more oxygens than the ite? How do I remember that? Yum, 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 yum. I ate 1 more oxygen than the ite. Get it? So those will always have 1 more oxygen, but it doesn't tell you how many oxygens, just that it's 1 more. So if you memorize all your 8 versions, then by default, you know all your ite versions, correct? And then there's a few, like your perchlorate version, and then your hypochlorite version. Those are here. So hypo is 2 less than the 8. Ite is 1 less than the 8. Then there's 8. Then there's the per-8, which is 1 more oxygen than the 8. I think of per as hyper, so it's 1 more. That's how I kind of remember that. But you can easily just memorize these. And they all carry the same charge. Oxxo anions, so oxygen-containing anions. So this is chlorate. So we have hypochlorite, chlorite, chlorate, and perchlorate. So if you memorize the chlorate version, you can sort of come up with the rest of them. You guys remember all this? All right, sulfate we know is SO4 minus 2. Sulfite then has to be SO3 minus 2. There is no hypo or per-8 version for this. All right, so here's another list of naming with polyatomic ions. So go for this, and then we'll come back. So the first one, number 1, Brian. Copper 2 carbonate, correct. Number 2, Andrew.
Sulfide.
Sulfite, correct. Number 3, Argo.
Calcium chloride.
Hypo.
Ah.
So it's only the one oxygen there. Calcium hypochlorite. Number 4, Mike Camp.
Potassium perchlorate.
Yep. Number 5, Allison.
Sodium chloride.
Yep. Number 6, Emily.
Lithium nitrate.
Nitrite, correct. Number 7, Grace.
Lithium nitrate.
Yep. And number 8, Brian.
Sodium
Acetate, yep. All right. Recognizing ionic compounds. Ionic compounds can either contain, no, they not either. They have to contain a metal and a nonmetal. That's how it works. But your polyatomic ions are your grouping of your nonmetals, so you can incorporate that into the definition. If the first word in the compound is a metal or ammonium, it is an ionic compound. This is so fundamental that you have to make sure that you carry this for the rest of the year. We're going to talk about intermolecular forces quite a bit early on, I think in like one more lecture or one more test set. If you can't identify that something's an ionic compound versus a molecular, you can't possibly answer advanced questions about intermolecular forces. So always say to yourself when looking at a compound, is the first element a metal or nonmetal? That's all you have to do, and then you can answer the rest of the questions. So just make sure you're looking at a periodic table and identifying if it's an ionic compound or not. Next, writing ionic formulas. Ionic compounds are neutral. I showed you their charges add up to 0 earlier. Charges come from the group in the periodic table, group 1's plus 1, group 2's plus 2, and so forth. And parentheses must be used when there is some multiple of certain polyatomic ions. We know this already. So calcium chloride, calcium's always a plus 2 charge, chloride's always a minus 1. Really fast. I mean, this is almost ridiculous, but we'll put it up here just to make sure. Ca plus 2, Cl minus, crisscross, you get Ca, Cl2. Make sure that you always reduce. So don't leave like a Mg2O2. That would be inappropriate, right? So we're going to cross those and just reduce to MgO. So formula units are always the lowest whole number ratio of the ions in the crystal lattice. So here's the crisscross method, and then writing them for a stock system, the charge is just given to you in the Roman numerals, so you're just going to write that charge. You group the polyatomic ions with parentheses, so take a look at this slide. So you have to put a 3 on the outside of the parentheses, otherwise it looks like 43 oxygens, right? Which one is the most common one that you're going to forget to put parentheses around? Most common is hydroxide, because it's easy to write hydroxide like this because you don't see that 43 or a 42. But you have to make sure that you group polyatomic ions with the OH. So hydroxide and cyanide are the 2 that are most commonly left off with for parentheses, so make sure you keep track of them. All right, so write the formulas for these. The first one might throw you for a loop because that's not one that you recognize, hydrogen sulfate. So let me just show you quickly, whenever you see a hydrogen added to a polyatomic ion, we know that sulfate is SO4 minus 2. You don't have to kind of memorize it, just recognize that if I add an H to this, H is a plus charge, it's going to remove one of these negative 2's. So I'm just sticking this together and it's HSO4 now minus. Follow that? Or you memorize it, or just recognize how the hydrogen plays into that. So we'll come back in a moment. So the first one, aluminum hydrogen sulfate. I'm just going to throw them up here because otherwise it's hard for us to read them. Al parentheses HSO4 parentheses 3. Iron 2 oxide is FeO. Number 3, Fe2O3. Number 4, SrCrO4. Number 5, KCl. 6, NH4NO3. 7, Li2SO3. Good?
Wait, so you don't need parentheses on the last thing too?
No. You don't need parentheses unless there's something written on the outside. So it's just unnecessary to put them on the outside. Sometimes people will write their SO4 minus 2 like this, and then they might group it in parentheses just to show that this is the polyatomic ion. But once you make the formula, there's no need for parentheses afterwards. All right, recognizing binary covalent compounds. What is a covalent compound? What does that make? A A molecule. What does an ionic compound make? A FU. Formula unit, right? So we have formula units are what ionic compounds are called. We have molecules that come from covalent compounds. So an ionic bond makes a formula unit. A covalent bond makes a molecule. Use the words correctly. So how do I recognize that I have a covalent bond or a molecule? It is between two or more nonmetals. So again, always look at your first element. If the first element's a metal, ionic. If the first element's a nonmetal, it has to be covalent because you would always write your metals first. All right, so 2 words with prefixes. You have to know your prefixes for this. So we have mono means 1, di means 2, tri means 3. 4 is the trigger. That's usually where students are like, oh, I can't remember what 4 is supposed to be. Tetra, like Tetris. You remember Tetris, when you play it, it's 4 blocks in different shapes. You can rotate them 4 ways, and the way that you clear it is when 4 of them match the same color. So 4, 4, 4, Tetris. So tetra. 5 is penta, 6 is hexa, 7 sometimes throws you for a loop too. It's hepta. 8 octa, 9 nona, I think of my grandma, and 10 deca. Got it? Those are the ones you gotta know. The first word takes the name of the element with the suitable prefix. We don't use mono if the first element is only 1. So carbon monoxide, CO is carbon monoxide, not monocarbon monoxide. So if the first element is just 1, we leave off the mono prefix. The second word takes the name of the element with the "ide" suffix and the suitable prefix. Remember those rules? So you still end it in "ide," which means that in a general rule, all binary compounds, whether they are ionic or covalent, always end in "ide." Make sense? Because a binary ionic would be just our elements, our anions on the periodic table that are carbon, nitrogen, oxygen, fluorine, and so forth. Those will always end in "ide." So all binary compounds end in "ide," whether they are ionic or covalent. So here's your list. Let's do these together. All right, so we have number 1, Nelson. Shh.
Silicon dioxide.
Silicon dioxide. Number 2, Mike Stewart.
Carbon monoxide.
Right. Number 3, Allison.
Carbon tetrafluoride.
Yep, carbon tetrafluoride. Number 4, Olivia. Tetranitrogen tetraoxide. Number 5, Argo.
Neon hexafluoride.
Yep. Number 6, Michaela.
Dinitrogen trioxide.
Yep. Number 7, Tasya.
Tetraphosphorus.
Heptaoxide. Yeah, you know, there's not really a rule, I've looked it up, for trying to find where the A and the O, like when do you cancel the double vowel? Sometimes it's appropriate, sometimes it's not. It just comes with, I guess, practice and hearing them, because there's not a specific set rule of when to drop the double vowels. So I'm not going to take off points for whether you said heptoxide or heptaoxide, okay? So there's your list. This one written heptaoxide. All right, writing molecular formulas now. So now you're taking those prefixes and just turning them into the subscripts. Do you crisscross for covalent when you're writing formulas? Never crisscross them. You just take the prefix and you jot it down as the subscript right away. So we'll come back to these. So we have carbon dioxide, CO2. Number 2, phosphorus trichloride is PCl3. Sulfur tetrafluoride, SF4. Disulfur dichloride, S2Cl2. Do we reduce? No, because these are molecules, which means that they are individual entities on their own, whereas a formula unit is a crystal lattice network with millions of them surrounding each other, and you just take the lowest whole number ratio of them. Iodine monochloride, ICl. Dinitrogen tetraoxide, N2O4. Nitrogen triiodide, Ni3. Notice the double vowel there. Okay? Recognizing acids. Simplest way, they start with an H, usually. The most common one that we end up using in this course doesn't start with an H. It's most commonly written like this. What is that? Acetic acid. It's the acetate ion with hydrogen. We don't write it like this. You're not going to see that. They're going to write it like this, and you need to recognize that it's an acid. Most commonly used, for sure. When we get to acids and bases, which is near the end of the year, or the end of the course, we will use acetic acid most frequently. So you just have to recognize that's acetic acid. It's an acid. But otherwise, most of them start with H, so you'll recognize that it's an acid because of that. For organic acids, the cation is often placed at the end, like acetic acid. And there are two types of acids that we will look at, acids that contain oxygen and acids that do not contain oxygen. Acids that contain oxygen we call oxo acids, because oxo meaning the oxygen. And we'll talk about these again with intermolecular forces later. So naming oxygen-containing acids. To name all the acids, you always look at the anion, because what's the cation always going to be? Hydrogen. Hydrogen's always your cation, H+, with a +1 charge. Oxygen-containing acids have polyatomic ions, because otherwise it would just be oxide, and that's not going to create your acid there. What would be? Then that would make water. H and OH would make water, H2O, which water can play as an acid or a base. Write the name of the polyatomic anion, but change it too. So here's your rule. If you have an 8, it turns to an ic. If you have an ite, it turns to an us. And then we'll get to, if you have an ide, that's your hydro and your ic. So the general rules are written here for you, but I'm going to write them up again. So if you have an 8, that equals an ic. If you have an ite, that equals an us. And if you have an ide, which we'll get to, is a hydro with an ic. So these are your endings. So here are the formulas. So let's just look at it. HClO4. Well, what is the name of ClO4? Perchlorate. It ends in an 8, so I need to change the 8 to an ic. So it's perchloric acid. Again, the where you drop the 8 or the ite and pick it up sometimes is a little tricky. H2SO4. SO4 minus 2 is sulfate. So if it's an 8, you pick up the ic. Sulfuric acid. Acetate, acetic acid. Sulfite. The ite gets dropped and you write an us. Sulfurous acid. That one's tricky for people because sometimes they want to say sulfus acid. But it's just hearing it and then remembering that it's supposed to be sulfurous acid. Nitrite, nitrous acid. Non-oxygen containing acids, this is the rule. You take the ide off, you add a hydro as the prefix, and add ic as your ending. So HCN, even though it's a polyatomic ion, it still ends in ide, so I'm going to call it hydrocyanic acid. HCl, chloride, hydrochloric acid. Br, bromide, hydrobromic acid. Easy enough? What's HF? Hydrofluoric acid. So write out the formulas. So for this one now, what are you going to do? You're going to crisscross just like you did for ionic, except your cation is always going to be the H+. And now you have to figure out what your anion is based on your endings. So the X, but pay attention, does it have a hydro in front of it? So now you're going to crisscross H+ with the anion that you know it should be. So nitric acid, an ic means that it came from an 8. I'm going to do this on the board just so you can see a few of them in case you're still confused. So an ic came from an 8. That's nitrate. So I crisscross that and I get HNO3. Phosphoric acid, ic, always pair it with the H+, came from phosphate. So that's H3PO4. Hydrofluoric, hydro and an ic, came from an ide, so that came from fluoride, which is F-, so it's HF. Hydrophosphoric, H3P, carbonic acid is H2CO3, and hypochlorous acid is HClO. Okay? Hydrates, almost done. Hydrates are ionic compounds that trap water within their structures. So we have our crystal lattice network, and then stuck within that network are water molecules, which we know are covalently bonded, but they're trapped inside there. Both the name and the chemical formula specify how much water is contained within the structure. And we'll use this in our next lectures to talk about percentage of water within a crystal lattice. So you need to know how much water is there before you can even calculate percent comp of the water. So writing formulas for hydrates, you use all the rules that you learned earlier for ionic compounds, and then you add a dot and the correct number of waters taken from the prefix. So for example, sodium sulfate, we already know sodium sulfate, Na+, sulfate, SO4 minus 2, crisscross, Na2SO4. But then it says decahydrate. So sodium sulfate decahydrate. Hydrate means water. So when you see the word hydrate, you write H2O. Deca means 10. You add a dot, then you write 10 H2O. So now I know that this is a hydrate with 10 waters trapped within this crystal lattice. Don't forget your dot, don't forget the 10, and hydrate's always water. Go ahead and do these two. Barium chloride dihydrate, write the formula, and then take this, number 2, and write the name. So barium chloride dihydrate, BaCl2 dot 2H2O. Thumbs up if you got that. All right, who wants the last one to name it? Go ahead, Emily.
Iron 3 chloride hexahydrate.
Yep, iron 3 chloride hexahydrate. Great, all done.